Morning, my beautiful students. Welcome back to our class, Chemistry 101, General Chemistry 1. We're entering the final stage of the class, and this is Module 5.1, the Module 5 series, 5.1, Theories of Acid-Base Reaction. So Module 5 is all about acid-base chemistry, an introduction to acid-base chemistry. So we are going to start with theories of acid-base reactions. I am Professor Engineer J.C. Way. Today is 29 September 2023. I hope you're going to enjoy this class. We'll look at introduction, we'll look at Lavoisier and Davy theory, Arrhenius theory, Bronsted and Lowry theory, Lewis theory, then we'll conclude. Acids and bases are characterized by certain chemical properties. So there are properties that a substance will exhibit, and we say that substance is an acid. And there are some properties another substance will exhibit, we say that substance is a base. A substance which is acidic, look at that, has a sour taste, but please, nobody says you should go and test any acid in the lab. One of the reasons for this, one of the reasons for these characteristics is organic acids. Some of the acids we find in, fruits like citrus fruits and so on. So that gives us that taste. Nobody says you should go and take something like probably nitric acid in the lab and test. That will be suicidal. You don't try that. Acidic substances also generally corrosive. You see that. So if you try that, then there will be problem. If you do that alone, you won't survive it, and that's why I said suicidal. People will say you have committed suicide because you're supposed to know, even as a science student. And also, acidic substances changes the color of indicators. Of course, I know you have done that. We're going to see that later in module either 5.5 or 5.4. But I know you've done some practicals that will let you know that these substances change the colors of indicators. Excuse me. It also reacts with carbonates to produce carbon dioxide. This is elementary. We all did this in our secondary school. And with more reactive metals to produce hydrogen. Similarly, substances described as alkaline or basic are known for their soapy feel. When you touch them with your hand, it looks like it's slippery, something like soap, which is usually attributed to the ability to hydrolyze the proteins on the skin, and also ability to neutralize the properties of acidic substances. So you can see we're talking about acid here, we're talking about base here. So basic substances or alkaline substances will neutralize the properties of acidic substances. A number of theories have been developed on acids and bases, and we're going to discuss those theories now. The first one is the Lavoisier and Davy theory. Now remember, some of these theories do not come out of willingness to say something. It comes out of the anxiety that somebody is doing an experiment and something happens. And you now be like, no, this is the reason for this. And at that time, nobody knows the actual reason. And it will be recorded until it continues. People now start doing experiments on that to confirm, just like what we did in electrochemistry concerning how voltaic pile came to exist, galvanism, animal electricity came to exist, and so on, until the works of people like Faraday, after Davy, and so on, to let us know when I start talking about cathodes, anodes, and so on. So the same thing is happening with acids and bases. So one of the first generalizations about acids, you see now, we'll say it's scarcely a theory. It's not a theory actually, but we're putting it up as a theory here so that we'll know, track the development of acid-base chemistry. Came from the great French scientist Antonio Lavoisier in 1777. he proposed that all acids contain oxygen. Can you imagine that? All acids contain oxygen. Well, at that point, that was exactly what the mind told him, and he said that, and it generated a lot of curiosity. So, having demonstrated that oxygen was the principal agent of combustion, he named the gas oxygen, meaning acid producer. This theory failed when it was found by Humphrey Davy that the so-called oxymuriatic acid was in fact hydrochloric acid and contained no oxygen. So you can imagine that. But we'll still mention the man's name. We'll still mention Lavoisier. He put up this. So when Davy found out that no, this is even hydrochloric acid and contain no oxygen. So the part of trying to say acids contain oxygen is nowhere there, not close at all. But we're mentioning it. So Davy in 1816 therefore proposed that all acids contain hydrogen, and this is a better generalization. Next is Arrhenius theory. Now, an acid is a substance which in aqueous solution ionizes to give hydrogen ion interlayer. That's among others. Look at hydrogen ion. So HCl that we have mentioned will ionize to give hydrogen ions and Cl minus. So it is not just only hydrogen ion, it will give out hydrogen ion and also give out another ion, and this HCl is there. So all the acids we know, H2SO4 will ionize to give hydrogen ion and SO4 2 minus. So check most of the acids, even though there are some acids or some substances that behave as acid that may not have hydrogen ion. That's why we want to trace all this theory. But hydrogen ion has a large charge, and the ratio of charge to radius and mass is very high. So usually we prefer to use hydrozonium ion, that is HCl. And this reaction too appears to look like HCl is reacting with water. But this is stem acid reaction, where H3O plus is hydrozonium ion or oxonium ion or hydronium ion. All these mean the same. Whether you call it hydrozonium, oxonium, or hydronium ion, we're still referring to H3O plus. Now, the above equation implies that the reaction is not merely dissociation or ionization, but that HCl is reacting with water. You see what I mean? So if you look at it, it looks like HCl is reacting with water. And that's why we talk about, aqueous reactions or aqueous phase. But this is a, acidic reaction, trying to show you that HCl will always release hydrozonium ion, which is equivalent to hydrogen ion in equation 1. Arrhenius defined a base. Now look at that. After that, he now made his own definition. Acid gives off hydrogen ion, but a base dissociates in solution to give hydroxyl ion. And we use a very simple base, sodium hydroxide, giving sodium ion and hydroxyl ion. So any substance which gives hydrogen dissociates to give hydroxyl ion, Arrhenius said is a base. We'll also see that there are some substances that are still basic but do not give out OH minus ions. So one big disadvantage of Arrhenius' definition of acids and bases is that his definition, his definition is tied to the solvent water. Everything you're talking about here is water. Water must be here. So where there is no water, it means that we won't talk about acid and bases, which is not true. So he did not consider non-aqueous solvents or reactions that do not involve water. He didn't consider that, and that's one of the big disadvantages of Arrhenius theory. The next theory is Bronsted and Lowry theory. Now, Bronsted and Lowry independently defined an acid as proton donor and the base as proton acceptor. Now, consider the reactions 4 and 5. Look at it. HCl plus water gives us H3O plus Cl minus, and Na3 plus water again. Now, in equation 4, HCl, the acid, donated a proton to water. Look at it. If you add one hydrogen to this water, you will get H3O plus. So the HCl donated its hydrogen, which is a proton, to water. While in equation 5, the base NH3 accepted a proton from water. Look at it. When you remove one hydrogen from here, put it here, it becomes NH4, and we'll have OH minus. So in these two, water is there too. Therefore, Bronsted and Lowry define an acid as any substance which donates a proton to another substance, while a base is regarded as a substance which accepts a proton from any other substance. That's their own theory. Now, in equation 4, water behaves as a base. Look at it properly, right? Look at our definition. Acid is any substance that donates a proton, and base accepts. So in equation 4, water accepted a proton, which means it's a base. In equation 5, water donated a proton, which means it's an acid. So by Bronsted and Lowry, water can act as a base and also act as an acid. The above division is more general than that of Arrhenius. So we see that Bronsted and Lowry is better than Arrhenius. So in equation 4, water behaves as a base, and in 5, it behaves as an acid. Such substances like water, which could behave as an acid or base, is called amphiprotic substance. So any substance that can behave as a base and also behave as an acid is what we call amphiprotic substance. Therefore, when water accepts a proton, it forms a hydrozonium ion and behaves as a base. When it loses a proton, the hydrozonium ion behaves as an acid, and that's what we call amphiprotic substances. Now we refer to such substances and its ions as conjugate acid-base pairs. Look at the acid, the conjugate base, then this is the proton that is released. So when this man releases a proton, what remains of it becomes a conjugate base of this acid. So we can therefore say that acid and its corresponding base is called conjugate acid-base pair. Look at other examples. This is acid, this is a base. When HCl reacts with water, now for this H3O4 to form, this water will collect, let me use that language so you understand, will collect this hydrogen here. It has accepted a proton, so it is a base, and forms a conjugate acid here. And then this acid here, which will donate its proton to water, is an acid, and it forms a conjugate base. The same thing happens here also. Thus, from Bronsted and Lowry concept, it implies that when an acid loses a proton, it forms a base. Can you see that? This HCl loses this proton, hydrogen here. It forms a base, Cl minus. Are we following? Now this base here accepts a proton here, right, and forms an acid. When a base accepts a proton, it forms an acid. An acid forms its conjugate base upon loss of proton, and a base forms its conjugate acid upon gain of proton. It is worthy of mention here that the conjugate base of strong it is worthy of mention here that the conjugate base of a strong acid is weak, e.g. Cl, which is a conjugate base of HCl, a strong acid, is a poor acceptor of proton. That is a weak base. On the other hand, also, the conjugate base of a weak acid is strong. So we can see that this relationship of conjugate base pairs allows for establishment of the acid and base strength. I'll move forward to another theory, the Lewis theory. G.N. Lewis in 1938 defined an acid as molecules or ions that can accept electron pair. You see, we have moved from proton now to electron pair from another molecule. A base, a substance that shares its electron pair with acid or another substance. So acids can accept and base can donate. Therefore, Lewis defined acid as electron pair acceptor and base electron pair donor. Now, he also defined an acid as a substance which forms covalent bond with a substance, that's base, by accepting from it lone pair of electron. And base, a substance which forms covalent bond or coordinate bond with a substance which is an acid by donating to it lone pair of electron. So we see that by Lewis' definition, ammonia is a base, while boron trifluoride is an acid. Now, if you go back, write the structure of ammonia, write the structure of boron trifluoride, and see whether you can see where the electron pair, of course, in ammonia, you see the electron pair in nitrogen, which it will donate to boron trifluoride, and you see the acid-base neutralization reaction. When a Lewis acid reacts with a Lewis base, a coordinate bond is formed. This is called neutralization reaction, even though there is no formation of water. You can see that now we are beginning to do more generalization. It is called a Lewis neutralization to differentiate it from normal neutralization. For example, ammonia can neutralize a proton, that is H plus ion, to form hydrozonium, as to form ammonium radical. Again, try and check this. Ammonia NH3, of course, will have lone pair of electron at the nitrogen, which will, it will donate to hydrogen plus. Hydrogen plus has lost its own electron, and then you form ammonium radical. Also, the acid-base pair Al3 plus and water can undergo Lewis neutralization by formation of 6 coordinate bonds, which is also similar to neutralization. That's equation 10 here. So Lewis acids which accept electron pairs are called electrophiles. Philos meaning lover, electron lover. So those that accept electrons, they love electrons. That's why they accept electrons. So Lewis acids are called electrophiles, while Lewis base are known as nucleophiles, proton lover. Proton is a positive center, so they love positive charge, while Lewis acids love electron, that's love negative centers. Lewis concept of acids and bases correlated and embrace many reactions. They embrace many reactions which even involve proton transfer. Therefore, it offers the most definition of acids and bases. So Lewis concept offers a better definition, more than Arrhenius, more than Bronsted and Lowry, more than even the scarcely theory put forward by Lavoisier and Davy. All right, thank you very much. We've looked at theories of acids and bases. We look at Lavoisier and Davy theory, Arrhenius theory, Bronsted and Lowry theory, and Lewis theory. And you can see how we got to the point of trying to establish the concept of conjugate acid-base pair. Also the concept of Lewis, by electron pair donation and electron pair acceptance. Thank you very much, and see you in the next class. Thank you.